welcome and thank you to everyone here. We are Conor Collins and Matt Benson from Synthesis AI. Today we're going to share our automated digital human workflow with you.
Hi, I'm Matthew Benson. I got started at Pixar Animation Studios, where I worked for many years, and then made the move over to tech. We're in 2021, and I've been with Synthesis AI ever since.
Yeah, and I'm a technical artist as well at Synthesis. I had a previous career in high-end retouching. I joined Synthesis in 2022 after shifting to CG about 6 years prior, and I currently co-organize the Portland Hug. So we work at Synthesis AI, where we work on various products that support the creation of synthetic data. In our case, we use the tech coming out of the visual effects industry to build and render out imagery and metadata to fulfill our clients' needs. Our mission statement is utilizing a mix of ML, Gen AI, traditional VFX workflows. We pioneer synthetic data technologies to build more capable and ethical AI. We literally wrote the book on synthetic data. You can see there it has over 70,000 downloads. And we have broad industry recognition for our work. We're also trusted by world-class customers. So for those not familiar with synthetic data, it's a relatively nascent field. We are essentially creating training data for ML models that is representative of real-world data, but is in fact synthetic. Typically, data operations require images of real people and large-scale labeling operations where people hand-label images. Bias is inherent in a lot of those training sets. One common example is a data set named Celeb A, which is nothing but pictures of celebrities, and they are largely male and white. Synthetic data can be used to solve the bias problems like this one. It also has a wide range of use cases: AR, VR, automotive, biometrics, and virtual try-on, to name a few. So, why do we build digital humans? One large reason is that it was a previously unsolved problem in the CV and ML space. Collecting real-world data on humans is hard and problematic. There are privacy, bias, cost, quality, and scale problems. We solve these issues by way of synthetic data. We aren't using real people. We specifically fill in the gaps created by bias. We lower costs as our labeling comes for free. Our quality is pixel perfect, and we scale dynamically. By the way, in addition to perfectly accurate data, we can also provide data that is impossible for humans to label by hand or eye. You know, these like AOVs, light direction, identical images at different times of day, normals, point position, and other geometric data. So scale is also a large problem. We solve this with our custom AWS pipeline. And here is an overview of that pipeline. Our engineers leverage AWS managed services and Kubernetes to achieve dynamic scalability. Here we can allocate scale across customer jobs to balance loads. We run rendering and scene generation in separate steps as well. The architecture is designed to allow each step to scale independently, preventing any bottlenecks that would result from a monolithic approach. And currently we're capable of serving millions of images per customer. So with this pipeline, internally crafted DAGs or verticals are connected, allowing for adaptable iteration and precise task triggering to be seamlessly managed. This is an example of a DAG used in our pipeline, and this is our identity creation vertical. So we'll start by sharing how we build identities and work our way towards the full asset. Conceptually, we structure our digital human assets like so. First, we create an identity, then we build an asset around that identity, and then we package that up for a specific application or endpoint. We use a spec-driven workflow where a JSON describes the ingredients to make the identity. This includes prompts that describe the identity, a seed for randomization, and various other job details. With that spec, we build a mesh from a custom ML mesh model. From that, we also generate depth passes. Images are generated in Comfy UI from those depth passes. The prompts and seed in the spec drive this step. We round trip the projection back onto the mesh as point clouds. The point color is composited together into one cohesive cloud that now has UVs. From here, we procedurally generate a texture set using split frequency techniques. And so now I'm going to go into each of those steps just a little bit closer. So our ML mesh model runs inside Houdini through a custom HDA. It runs on a custom Python environment. We trained that model in-house. And it maintains a lot of libraries and versions involved that when you get down to it can be a little bit tricky. Anyone maintaining multiple PyTorch or CUDA versions will have familiarity with this. I got one laugh, someone knows. Okay, so this generates a mesh by sampling the latent space of our training data, which includes an extensive scan database, all built around our standardized topology. To control this further, we have specific submodels for demographics that we match via our JSON spec coming in. And once we have this mesh, we can then render out depth passes and send those out for diffusion in Comfy UI. Our diffusion process generates a wide range of age, sex, and ancestry across our identities. We can oversample into specific demographics and increase diversity just in that group. Reducing the bias present in ML models is part of our stated goals, and this is one of the ways we achieve it. So the depth passes allow us to tightly control faces generated, close enough to project the images back onto the mesh used to create it. This is how we create our core identity for every prompt. And using standardized inputs, we hope to get back unique identities. We use diffusion models to generate all of our identities in Comfy UI, but don't worry, we still work procedurally outside of Houdini. Comfy UI is fascinating, and we have put a lot of development into it over the past year. We built custom tools and nodes, just like you would in Houdini. So the images made in Comfy UI are going to eventually become our diffuse texture and add detail to the texture set. After the identities are inferred, we jump right back into Houdini to finish it up. And this is where we build the textures using a process of point cloud compositing. Image planes are projected back onto the head mesh using a straightforward ray sop. And because we're in Houdini, we made sure just to play around Vex just for this presentation. This is our projection and weights HDA that set up each image plane. It takes in the camera plane with focal point normals, the center ray of the camera, and the head model used to create the identity. We then calculate a composite weight score that is composed from several attributes based on all the geometry in play. It's roughly about 1.5 million points at this point from a single image plane. And you can see over here we have a HDA where we can just turn off attributes and then calculate the weight from a formula of those attributes. And this is like the high frequency of point position attribute. I'm just going to visualize a couple of them here. Custom masks that you can create like that, Fresnel. And then distance from the center ray of the focal point of the camera, which you can see is sort of like a ray going from the camera through the model and then the distance from that ray. And depth, plus a lot more. From there, we take all the point clouds with all their weights and color and merge them together. There we are, merging them. Then we delight this a little bit. Right here. You can see there's the normal color and there's the delight color that's using a delight node. Then we combine this color along with some generalized point color for coverage across the whole surface, which happens right there. We merge them all back together again. And we use a PC open function to average the color weighted. We weight the average color in 3D space, and that's how we get the final color. We use a larger radius for the PC open function to get a low frequency pass, which you can see there, it's a little bit softer right there. And then we also create a high frequency pass here, which gets multiplied back into the low pass. And when they get multiplied back together, right there, that's how we get our composite color. So the only thing left to do here is to unwrap these points into UV space, which we got from the ray sop. Eventually. There you go. And once we have that unwrapped, we can transfer that color detail to a grid that is set to our texture output resolution, like so. And now it's time to build the texture sets from this composite color. But I want to do a small primer on frequency separation or split frequency techniques. You can break frequencies of an image apart by use of a kernel image. Here, a blurred image on the bottom there is used as a low frequency, and we divide that into the original image to pull out the remaining high frequency details. You can break them apart and put them back together again with no loss. This allows us to work on skin tone and skin detail separately. We use this technique extensively across 2D and 3D portions of our identity workflow. And using this technique alone on the 2D images, we can combinatorially expand our scan textures dramatically. We build the textures in COPs, old COPs. This heavily takes advantage of our static UV layouts and topology. Because all facial features are in similar locations, we can use them like puzzle pieces. Normals, glossy, and specular textures are created from the diffuse texture and blended with mesh and scan details. At this step, we save out a Q-ray render, and we can see all the work in one image. And that's how we create the identity. Key metadata and demographics are built here, and now we start building the asset, is where I pass off to Matt.
Hey. Yeah, so at this point, we've got a nice diffused mesh and texture set for our head, but we still have a long way to go until this is usable data that we can start using to train machine learning vision models. So this next part of the presentation takes us from the diffused head all the way to a full USD asset that can be packaged up and sent to clients across various software packages. So we'll start with the body. And luckily for us, the head already has a huge amount of metadata already baked in. We've got age, sex, BMI, ethnicity, Monk score, and all of these things are going to be stored as detail attributes. We additionally will weigh certain attributes higher or lower based on which attributes seem to be the best predictors of an accurate body match. This metadata, especially around demographics, is going to be kept with us for the entirety of this process because it's incredibly important for future ML training. So at this step, we use the metadata from the head, and we start looking into our vast library of scanned bodies, and we filter those down into relevant sample pools. Once we get a relevant sample pool, we use a radial bias function to create a unique and correlated body shape. It's after this that we start fitting that head with teeth, tongues, high-resolution eyeball models, eyelashes, etc. Now, at the end of the day, we're still working with scan data for the bodies specifically, and not every actor is going to know how to stand in a perfect A pose. And even if they could, it's not going to match someone else's perfect A pose. Therefore, we came up with a procedural way to adjust the poses into a standardized A pose. By having this completely procedural, we're enabled to do faster iterations with new body shapes and even start importing things from multiple different sources into our pipeline quite easily. It works pretty simply by putting a point cloud on known coordinates across the body and then sort of growing an armature from that. We then use kineffects to morph the body into our idealized A position. So yeah, after that step, our body is now in the A pose that we desire it to be in. And from there, it's really easy, thanks to our unified topology, to move a kineffects rig into the updated position for any novel body that we create from this point forward. So the last step in the body creation process is prepping the textures and meshes and then getting them into Solaris so that they can be packaged up. The first step is skin color matching. So even though we have a really varied array of scanned textures, the skin tone is never going to perfectly match this completely unique diffused head. And as a result, we do a little bit of color moving to move it into the correct color space so that it's a much closer match for that diffused head. After that, we go back up to the head and we take sections of that body and we blur it into the head texture. And this is often quite subtle to see, but it's really important to prevent any visual seams from being visible in the final asset. In this particular example, you can see that there's a little bit of pink near the clavicle, and so we blur that out using the new body texture. And now we're ready to get into Solaris, this is where we do final look development, materials, subsurface, all that gets set up in here, and then we do an export to USD, and we also do a QA render at this point. So we do a tight QA render on the head, and then a looser one that you are seeing here, and that enables us to generate hundreds of IDs, and then quickly iterate through them to make sure that they look, good and how we expect them to look. Next step is clothing. Before I begin, I want to quickly go over some of the vernacular that I'm going to be using, because synthesis uses them kind of differently from how you might be used to hearing them. So for us, garments are the individual layers that make up an outfit. So you can think of this as just jeans or just t-shirt, jackets, scarves, etc. And an outfit is going to be a combination of those garments. And these are often constructed in a JSON file, and for us, order really matters, because in our pipeline, t-shirt comma jeans would result in a t-shirt that's tucked into the jeans, while jeans comma t-shirt would be a casual t-shirt resting on top of the jeans. And finally is our wardrobe. This is a collection of pre-calculated outfits that are ready to go and ready to be fit on any novel body that we might throw at it. At Synthesis, diversity is king, and so we have literally hundreds of garments, and each one of those garments can have 20 to 30 texture variations, and each outfit can support from 2 to 5 layers. And technically we can go up to n number of layers, but they start looking really ridiculous at a certain point, so we cut it off at 5. And because of this, we're able to offer our clients literally millions of possible outfits. And it's because of those millions of possible variations that we decided to create subsections of our wardrobe, and we refer to these as styles. And as a client might come up to us, they will tell us what kind of job they're looking for. For example, construction safety. We can say, hey, we've got a whole wardrobe of construction safety that you can take a look at, or formal or athletic wear, whatever they might be looking to do. Our outfit creator is actually the only bit of this presentation that doesn't live in one streamlined process, and that's because it's a separate HIP file entirely. It has a nice UI at the front that allows users to add garments to a list, name the outfit, and then quickly export it to the wardrobe. This also can be entirely automated by simply importing a directory of JSON files, and this enables artists to write a script that might make hundreds of outfits for a specific job or client that might come through. This is an example. As you can see, the wardrobe has the shirt comma shorts, and then shorts comma shirt, and you can see the variation that we get therein. The outfit creator directly links to a Python script, so whenever you add a layer, it adds a layer node directly inside of that HDA. And inside of those layer nodes is what we refer to as the fit network, and we don't have nearly enough time to go into all of this, but we'll do the best we can. In this example, we've got a t-shirt that needs to get tucked into shorts, and so because this is a very expensive operation, we first figure out what area would actually be inside of the shorts, and we do this by simply calculating the total volume of all previous layers and then selecting points within that range. We then look at the previous layers and we determine a stretching direction based on the input body, and we stretch out that layer, and that gives us 2 poses, stretched out and normal rest pose. And we use both of these to be fed into a detangle node, along with the next layer, in this case, a t-shirt. And what that does is it sort of squishes the t-shirt so that it fits within the shorts, so that there's no overlap and it just sort of like compresses. As some of you might have noticed if you're in CFX, that looks kind of gross and it's very sharp, and cloth doesn't do that. So the next step is we delta mush it back to the original shape and we smooth all of that out. Next, we bring the body back in and we push that t-shirt out. And some of you might be thinking, well, that doesn't work. That undid all of the work that you just did. And it does. So we do that inside of a loop, and we do that about 12 to 14 times, and it eventually gives us this really soft, but still compressed look on our garments. Once it's exported to the wardrobe, we now have an outfit that's ready to be just put onto any novel body that we could throw on it. And this is a relatively cheap process, and as a result, it can live back in that main vertical that we've been talking about this whole time. Next is hair, masks, and hats. So most of our clients are still primarily interested in facial data and head data. And there's still a lot that goes into that beyond just a textured head. We've got to add hair, facial hair, eyebrows, headwear, masks, etc. Our hair works very similarly to the clothing in that you get a UI and that on the fly we'll add layers to that HDA. So here we've added some head hair, we've added eyebrows of a certain style, and we've added some facial hair. We can also quickly add headwear. We've got a vast library of headwear options, and these get added actually as USD overlays so that we can quickly iterate through them on the fly as we're rendering, and very similar for masks. We found that these were actually incredibly useful during the pandemic when traditional data sources were kind of struggling to safely capture massive amounts of people wearing masks. Everybody was kind of sheltered in place, and we were able to quickly spin this up and get this data right to clients so that they could start learning what does a face look like when it's covered in this type of mask or that kind of mask, or even people not wearing masks correctly. So the last step is we've got our person, they've got hair, they've got clothing, and they're all rigged. What do we do from here? Well, the final step is to organize all of the relevant data and get it into a directory so that we can zip it up and send it to clients. Our texture path resolver basically runs a series of Python scripts that run through our database and find any textures that this particular body might be referencing. So that body textures, head textures, every single garment has its own metallic, roughness, bump maps, etc., and those need to get processed. And finally, we also set up a bunch of sidecar files that make things like Unreal a lot happier. So yeah, this enables us to have really compatible characters. Our characters work obviously natively inside of Solaris because that's where we built them, but they also work inside of Unreal Engine and Omniverse as well. And that's how we automate building digital humans at Synthesis AI. Yeah. Thank you.
So going forward, because of the flexible nature of our pipeline, we can iterate and augment over any of these steps and improve them over time. And we're looking at all sorts of different ways to do that. Performance, implement new tech like Gaussian splatting or flux models. We want to improve our ML models and convert them to native PCA nodes, maybe in the future. We have R&D ideas like text to directed animation or UV control nets. Also, ML skin and clothing deformers or Apex rigging integration are all things we're looking at. And thank you. We are Matt Benson and Conor Collins.
Thanks, guys. Does anyone have any questions?
Lots of questions.
Okay. X-ray.
When you're generating a synthetic data set like that, how do you ensure that you're not introducing bias accidentally and maintaining a ground truth?
Do you want me to take that or do you go for it? Yeah, so what we do is, luckily for us, we have access to the entire demographics that we're about to send to a client. So what we can do is if our, you can imagine like a pie chart. If our pie chart is coming up empty in a particular area, we can infuse that with more data that would fill out that particular piece. Now, of course, all of our data is, n-dimensional, right? It's not just, men versus women in the pie chart. There's also ethnicity, BMI. And so we do look at each of these dimensions that at least we're able to tell might influence a ML model. And then we try our best to make sure that we have a unified curve structure across that would represent.
And I understand that statistically that's correct, but the actual data that you have, you're generating synthetic ethnicities. Mm-hmm. How do you know that you're getting those correct, that it's actual ground truth and you're not introducing artifacts from getting something about an ethnicity wrong, for example?
There's certain artifacts that can come from say the ML models, like SDXL or something like that. But we're also layering those onto 3D meshes on top of that. So there's several layers in between. It is a concern, and we look at as many metrics as we can. So it's something we want to continue working on.
It's kind of the mission of the company is
Yeah.
to reduce that as much as possible.
Yeah.
And so it's an ongoing process. It's not something that, there's no perfect end date of that question. I think it's something that we work for, day after day to try to reduce it as much as we can.
There were some, okay.
I have a question regarding UVs. So do you end up with unique UVs per each iteration, or so it is consistent between?
Yeah.
Okay.
We have like a single UV topology that is across all of our identities.
And do you have to provide some sort of textures in the beginning? I assume you have to, right?
Say that again?
So you have to give it some textures, and then it just processes it and creates something out of it, right? So you can't just start with nothing.
No, we're using versions of SCXL models to create this too. We haven't completely trained a base SDXL model, so we're using versions of that to create the textures. But yeah, we do use portions of scan textures as well to fill things in. You can see that we're doing 4 image planes there. We could do it for the whole entire head, but for efficiency's sake, we're focusing on the mask.
Okay.
Yeah.
And are you able to create different resolutions?
Yes.
Oh, that's cool.
Yeah.
Any limitations there?
The point cloud limitations in Houdini.
Okay.
The GPU RAM of modern GPUs is a limitation. You can do various upscaling things to get larger images. So it's possible to make these things huge and get really high-res textures. Yeah, so there's a lot there.
Yeah, that's cool. Thanks.
So you mentioned that you generate a bunch of textures from Stable Diffusion. So how do you manage them to be consistent for one phase? You use some control nets to make, or IP adapter to make sure that you have, for example, this facial main camera, and then you use it as a reference for all others. Do you have any issues if you have a mole, for example, somewhere on the face? Will it be the same across all those different views?
Yeah, so we use tools that take advantage of the Insight Face library, and there's a lot of tools like that, like Reactor or Pull ID. We've found pretty close control over different images, even wrinkle lines, laugh lines, moles. Those things will transfer to different views as long as we have a good generated identity to transfer via Insight Face.
That's cool. And thank you. And another question is, have it ever happened to you that you generate a person and you're like, oh my God, I know this guy, this is my buddy John or whatever?
That has not yet happened to happen, no. I haven't known anybody in our identities. Yeah.
Thank you.
Hello. Really interesting thing. There was a slide in between where all the details of the face were stored in the details node, details parameters like the face fat and everything. So does it apply to the rest of the body too?
Yes.
As you said, it will use all the elements from there.
Yeah, so as I said, luckily we kind of make the heads ourselves, so we get a lot of data that we're able to store based on that. And that creates a search within our database of scanned assets. So we're still using scanned for the base of the bodies. And we use that almost as search parameters. So we say, give me a representative pool of bodies that would fit within these scoped detail attributes. And then from a small representative pool, we'll use a radial bias function to sort of create a unique hybrid version of all of those. That's something unique to that head. But yeah, it does filter through. So if you get a particular BMI, the person is going to be skinnier or larger and older.
So just a follow-up question: if a human has a really low body fat, has like abs and biceps. So will it like be visible in the whole body?
Yeah, we've got a pretty representative body sampling size. We're continuing to try to grow that as we go. And the reason we do a representative pool is because BMI, as I'm sure you know, is not a great indicator of how the person is going to look. Some people have a low BMI and are just really skinny, and some people have low BMI but are just like, ripped. And that's why we sort of do a representative pool across many different attributes to try to get a body that would match that head well. In the future, who knows, we might be diffusing those too, but for now, that's sort of our best stab at how to get an accurate body based on the diffused head.
And we can add those details in the prompt also, like a really fit man of age 25, 26. Like, yeah, we can start with that.
Yeah.
Thank you.
Yeah.
All right, really amazing presentation. I love it. It's really interesting how you guys can create new humans, but I wonder if I have a shoot and I was not able to do a body capture of my actor, can I just bring in a couple of images and you guys get me an interesting body?
We've done some experimentation into that. There's obviously ethical concerns with that. Somebody might request a body that is not theirs, and that's extremely unethical, obviously, especially because, we are able to put clothes on a person. You can imagine that's not what we would want to get out into the general public. So we definitely steer far, far away from body doubles. But we have done experiments just to see what our stuff is capable of. Our CEO was generous enough to lend his face for one of these experiments. But yeah, we are aware of how the technology would affect our pipeline. I think the ethical concerns right now are something that we're currently navigating.
All right, thank you so much.
You've used Comfy UI for some stuff like diffuse. Have you considered like training 3D data and something like that?
We do in-house. Our head mesh model is from a PCA model.
Oh, okay.
Yeah. So we have trained on scan data.
Yeah. What was the results of training 3D data?
The results are everything you're seeing. So the head mesh is basically a latent space of all our scan data, and we can kind of, we get eigenvectors out of it, and we can sample them and get a very large strata of heads out of it.
Okay, thank you.
Thank you for the presentation, by the way, it's very fascinating work. I was curious if you ever had requests from your clients to add scaring or invalidities in the bodies that you're generating, or everybody's are supposed to be like perfect in a way, we don't see I know it's a bit weird, but maybe people with just one limb or people with more facial details.
Yeah, so as of right now, unfortunately, we are limited by the scan data available. However, that is an ongoing point that we would like to solve. I mean, the mission statement is to solve diversity gaps in current data sets, and that is a huge one that we are aware of and that we would like to move into. I think another thing that we would love to do is also people that might appear to have, able-bodied, but might walk with a limp. How do we represent that using maybe kineffects to affect the animation that we bring in? How would that affect, safety and stuff on a work site? If somebody's injured, that'd be good to know.
And so as a follow-up to that question, do you find yourself in a situation where you're working with your clients and you give them synthetic data, and then you realize that they still have to test the validity of their system with real people? Or are you still able to get into a position where they fully trust the output of the system based on your data?
I think a lot of times our data is supplemental to real data. So it's always living either side by side or together. With that, I think we work pretty closely with clients to teach them how to even use our data. Yeah.
And one last question, sorry. Do you know if at the moment when you're working with your clients, let's say if they want a pool of 2,000 characters, are you going to generate 2,000 new characters just for that client? Or you have your own library and you're reusing bodies from client to client?
So right now, we do generate often bespoke for clients. However, as our sample sizes get larger, as people start asking us for 200, 300,000 unique people, there's definitely some work to be done in creating a library of that. Yeah.
Awesome. Thank you very much.
Hello. So obviously your work is currently geared towards producing humans. Do you have ideas for extending it for demi-humans or more alien features?
Not at this time, but that would be fun if you could just extend it in any direction like that.
There has been a test where I made an orc. But it's not built to do that. Yeah.
But it did work.
It did work.
Yeah.
It did work. Yeah.
And just curious, start to finish, how long does it take currently to generate?
Why don't you answer for yours and I'll answer for mine?
So there's different pieces of it. From start to finish, the identity asset is anywhere from 5 to 20 minutes. Yeah.
That's nice.
And the rest is about 1 minute and 9 seconds. So.
Yes, exactly.
All right, thanks.
I'm wondering if you could elaborate a bit more on the PCA model and the generation of the head mesh. Go into some more detail on that. I'm really curious.
Anything specific?
I don't even know what questions to ask, to be honest.
Sure, yeah. So our ML engineers created the model. They trained it very specifically, and we built an HDA around it. And so what we do is we basically have 3 features that go into it that are at a variable, like age, fitness, or a spectrum of male, female in there. And we get out the mesh from that. And we have a series of eigenvectors, I said. There are about 50 to 100 of them. And those are trained on all those different little features. And they get randomized, and we can create new heads out of that. In the slide, you can see it. There's just like a big list of parameters. And they're ordered from largest effect to smallest effect. So some of them might do something just like move a nose left and right like that, because one model had a nose to the right. So,
yeah. Is that built off of like a set of scan 3D? Is that built off of a set of scan 3D data that you then trained on, and you're able to generate a consistent topology mesh out of it? Is that?
That's exactly right.
So was there like a GAN at the end that like made sure the mesh was the same, or?
No, not that I know of.
How did you guarantee that each one of them would have the same topology when it came out of the model?
We feed in a base topology to it, and it changes the point positions.
Okay, like an eigenface or something? Okay.
So it's also based off of a certain face, too. We use an averaged head of all the scanned heads, and that is sort of a middle point to all of our scanned heads. Okay. Anything else?
And okay, so the PCA model, I don't know anything about that as a model. Yeah. What is a PCA model?
It stands for point component analysis. We can talk more. I didn't build the PCA, I didn't train the model, so there's more I can talk to you about. I can also redirect you to the guy who did build it.
There's also a presentation coming up later that will explain that.
Oh, yeah. Oh, wait.
Are there any other questions? No? Okay. Oh. Just wait a sec.
Are you done with like scanning head models, or you are continuing it? Like you said, like you have enough to find the average middle point? So
no, we're always adding to our data set. That's part of the reason we built this whole thing to be very modular. We can add more bodies into our library. We would add more heads in potentially. Yeah, I mean, we're always just trying to grow the scanned seed stuff. And we do have certain things that show us where we might be lacking in certain areas, and we will try to fill those out as we discover holes or gaps. I mean, it is a huge n-dimensional thing that defines what a face looks like, and so we're always discovering new areas or new ways that we can fill in gaps.
Thank you.
Thank you.
So how large was your scan database so that you were able to train the model? Like how many different humans you have there, and how do you mark this data? Like all these parameters. Like do you the scans yourself and you measure people's heights and stuff, or you get this from somewhere?
So we're not actually allowed to say how many scans we are currently in possession of, but what was the second part that I might be able to answer?
How do you mark down this data? Like how do you get the prompts? Like
during the scanning process. Yeah.
So you do this in-house and not purchase it from anywhere, you just do it?
It is not, we do use third-party providers, and we use a multitude of different, and that's yet again another reason we built this out. It takes in multiple inputs from many different houses that do this type of work, and they help us with the markdown of all the relevant data that we might need. But yeah.
Thank you.
And that's all the time we have questions for. Thank you, Conor and Matthew.
Thank you.